Alright, so welcome everyone to the grand finale of this year's ISEM lectures. La Grand Finale, lecture 14, the second part of the proof of the Kato conjecture. Okay, so as you can probably already hear from my voice, I'm not in the best shape that I could be because I fell sick over the weekend. I just recovered enough to give this lecture for you nonetheless. I also promised to my daughter, who also fell sick, that I would say hi to her in one of the videos, so I'm going to do this, and this time cameraman is not going to cut it out. So, hallo Rosalie. That's it. That's for her. And so, back to business. So, it's the second part of the proof of the Kato conjecture. Okay, and so, if we want to start, we should sort of wrap up on the things that happened last time in part 1. Okay, and so I remind you that the ultimate goal was to prove a square function estimate, which looked like this. Okay, so it's the integral from 0 to infinity, theta of t, grad of u, 2 norm squared, dt over t, that should be bounded by the gradient of u in L2 norm. Okay? So that was the reduction that has been achieved in lecture 12. That was Sylvie's part. We reduced the Kato conjecture, that is to determine the domain of the square root of L, an elliptic operator and divergence form on whole space Rn, to be equal to the form domain, that is the first order Sobolev space. We attacked this problem via square function estimates, and then at the beginning of part 1 we reformulated the square function estimate using this operator's theta. Okay, and so that was because we wanted to think, at least in parts, of this grad of u as just being a vector valued L2 function f. Okay, and the theta was a particular family of operators, so theta of t was minus t, the resolvent, or to be more precise, the inverse of the curly operator L diff of A. Okay, so theta of f would be diff of A f. Okay? That was theta. And so the goal was to prove this square function estimate. So last time we did two things. We did something that we called principal part approximation. Okay, and this principal part approximation, that was about comparing theta to a family of operators that sort of act as multiplication operators with a particular function on the dyadic averages. Okay? Some sort of discretization of theta of t on each dyadic crit of scale t. And t is the same as the t that is integrated here. Okay, so that was the first thing. And then once we had achieved this principal part approximation, we wrote out the square function estimate for the remaining term. And we realized that this brought us back to lecture 9 when we talked about Carlson measures. Okay? And so, all in all, in corollary 1316, we had reduced the matter, okay, reduced to, well, initially I said, and this is how we formulated in the lecture, we reduced to a Carlson measure estimate. Okay? Now I want to make a slight twist in perspective on what that meant, that we reduced to a Carlson measure estimate. Okay? And what I claim is that think of this as bounding a certain quantity t, call it capital T. It's a certain quantity, like an operator, acting on this function f. Okay, and so we want to prove the boundedness of that thing that is applied to f, because we want to control something where we do something with the f just by the L2 norm of f. Okay? So think of that as being the L2 boundedness of an operator. Then I claim that so far we have managed to prove that bounding this particular operator acting on all these vector valued functions f is equivalent to investigating the operator on very, very specific functions. Okay? So I claim that we reduced to investigating theta t on very specific f. Do you recall which f I have to take? Well, we reduced it to the principal part being linked to a Carlson measure, and the principal part was the application of theta to these constant functions pointing just in the coordinate direction. Okay, so in this sense, we have reduced to investigating theta on very specific f, namely f being eta 1, eta 2, and so on until eta n, which correspond to the principal part. Okay, and so the principal part, gamma t, was defined as the collection of all these applications, theta t applied to the coordinate functions, j running from 1 to n. Okay, that's a different perspective. Instead of proving the bound for all f, we take a very limited set, n functions. In particular, when I'm in dimension 1, I have reduced the matter to proving a property for theta t of the one function alone. Okay? And so we have reduced to investigating, and what does investigating mean? Okay? Investigating means proving that something is a Carlson measure. Okay? So investigating means gamma of t x squared dx dt over t should be a Carlson measure. Okay. So that's kind of the picture that you have in mind. Okay, so that thing is not new. That sort of reduction was known long before the proof of the Kato conjecture. Okay, and we call this a T of 1 theorem if we do a thing like this. Okay, so that is called a T1 theorem. And this goes back to the work of David and Journet from 84, I think. Should look it up. Yeah, that's correct. Okay. So why is it called a T of 1 theorem? Well, if you think of dimension 1, at least, then the boundedness of this quantity on the left-hand side, call it T, is reduced or actually being equivalent to proving something for t applied to the one function. Therefore, it's called the T of 1 theorem. Okay, and now that's one possibility. Okay, and what we have to prove for the T of 1 is this property. So this one would call the T of 1 property for theta t. Okay. So far so good. The T of 1 theorem is actually an equivalence, just as in lecture 13. So there is no way proving the Kato conjecture without making this Carlson measure estimate, hence without proving the required property for theta t of 1. Okay, but there is an issue. The issue is it might just be impossible to compute T of 1 or theta t of 1 or gamma t to an accuracy that is sufficient for proving this Carlson measure estimate. Because this Carlson measure estimate is not about global L2 norms, but it's really about zooming in into the pointwise values of this function. Okay, it might just be impossible to compute gamma t that good that we can prove this theorem. And so then this equivalence is true, but it's completely useless in order to complete the proof of the theorem. Okay? And so that's bad news. And actually, to make the news even worse, this is exactly what's going to happen for our theta t. So the way out is what people call the TB theorem. Okay. So TB theorem that appeared in the case of, I should say, the T of 1 theorem by David and Journet. That was not for this kind of things, and this is an O, by the way. It was not for this kind of quantities, but it was for singular integral operators. So if you've never heard about singular integral operators, just forget. Just think of something that in your mind resembles an integral operator and you're fine for the story. Okay? And we're not going to use any of these results. We're just going to be inspired by the strategy and the ideas behind this result to give a full and self-contained proof in this lecture. Okay, so don't be scared. Okay, and then there's this T of B theorems. This is David, Journet, and Sems from 87. Now, what's the idea behind a TB theorem? The idea is that, what is strange about the T1 theorem in a way is that you reduce it to one special function. That's sort of fantastic. But it's always the same function, no matter which operator T you take. All right, so the idea behind the TB theorem is, wouldn't it be better or wouldn't it be more accurate in applications to reduce, like in the T of 1 thing, but where 1 is replaced by a function b that I can still adjust using properties of the operator itself. Okay? So in the TB thing, the idea is B is tailored to T. Okay, and one calls a TB type test function. Okay, so the same sort of reduction, but you reduce it to a function that you can choose using properties of the operator itself. It could even be that when you try to prove this Carlson measure estimate, then this is some sort of uniform estimate quantified over all cubes. It could even be that the function b also depends on the cube. Then sometimes we call this a local TB theorem and so on and so forth. Okay, so I could go on like this forever with history, but we're not assuming any pre-knowledge on this. Okay, so this is kind of pointless. So what I will do instead is the following. So first I will fix notation for the rest of the lecture. And notation is exactly the same as in previous lectures. Okay, so C is always going to be, capital C and small c are always going to be positive constants that only depending on n, lambda, and lambda. And then, because this lecture we're seriously working with Carlson measures and Carlson boxes, I give a name to the Carlson box. R of Q is the cross product of Q and the half open interval reaching out to length of Q. This is the Carlson box over dyadic cube Q in square. Okay? And so instead of going on with the history and telling you things that you won't understand because you've never heard about them before, I will just try to give you an impression of what is going on with these T of B theorems by proving the Kato conjecture in dimension n is equal to 1 first. Because things are going to be much simpler. I hope that you get a beautiful overview on what the general idea is, why the T of B type procedure works, whereas the T of 1 thing would be hard to do. Okay, you will also see that actually we're using the test function B in order to verify the T1 condition in the end. Okay, then we're going to wrap up what we've seen. We're going to try to single out the essential problems that would appear when we go to higher dimensions. Then it's over for today, and higher dimensions we're going to do on Wednesday. Okay? So, if you've never heard about any of these T1, TB things, you're going to hopefully get at least the gist of the matter when we do the proof in dimension 1. Okay, so this is a T of B strategy for the Kato conjecture. Okay, so in this section, ambient dimension is 1. Okay, and what I claim, what we're going to prove today is the following proposition. It's the Carlson measure estimate in dimension n is equal to 1. So in dimension n is equal to 1, let's quickly recall what does it mean that this thing is a Carlson measure. Well, it means that the double integral over this Carlson box RQ gamma t of x squared dx dt over t. This is controlled by a constant times q. And that should work for every dyadic cube. Okay. You've been super quiet today, so either you're scared to breathe because I told you that I was sick, or it's fascinating, or you're tired. I hope I just guess that it's number 2. You're just so fascinating seeing that proof that you can barely say anything. Okay, so stay with me for the proof. So I need one lemma. I need one lemma before, and this lemma is going to be left as an exercise. Okay, and the lemma is, it sounds rather technical. Maybe when I write it down, you also think that it's not interesting at all, but it already uses in essential way the fact that we're in dimension 1. Okay? And what this lemma says is that in dimension 1, you recall that there was this principal part approximation. Okay, so the principal part approximation, that was which proposition? 1315. Okay. This principal part approximation was formulated not for arbitrary vector fields F, but it was also only formulated and proved for gradient fields. And we used that in an essential way in the proof when we applied some reproducing formula. Okay? But I claim that in dimension 1, the principal part approximation that we've seen in lecture 13 remains valid for every vector field F in L2. Okay? So this remains valid for all f in L2. Not just f being a gradient. Okay? So gradient here would actually be just a weak derivative. Forget about that. That's also a thing. When I do the proof now, I keep on using notation from the n-dimensional setting because I want to show you all the things I'm doing, and you could slightly be distracted when I replace divergences and gradients by just the x derivative. Of course, I know that in one dimension, gradient is just a derivative. Okay, and that's a thing that basically works because in one dimension this is just a derivative, and then okay, you're going to prove it. Okay, but this doesn't impose a structure on the vector field because it's just one component. Okay, so the proof of this is left as an exercise. It's one of the exercises accompanying the lecture. Okay, and so we're going to use that in the proof, and I'm going to show you exactly where we're going to use it and why we need the extended version. Okay, so now let's kick in and start the proof of 14.2. Okay, so I'm gonna prove this estimate cube by cube. Okay, so I'm gonna fix Q. And then I'm gonna prove this estimate by using a test function. Okay, and test function here doesn't refer to CC infinity, it just refers to a function that I'm using to somehow test the quality of my operator. Okay, and so I'm gonna use a test function that is adapted to this cube that I fixed at the beginning. Okay, and the picture is, it starts as usual, right? So it's in one dimension. So this is Q. Then you're gonna have 2 times Q. It's the larger cube. Gonna need some colors. Okay, then think of this as being a coordinate system. And then 2 times Q is this larger cube. Okay, so this is 2 times Q. And then you take the usual Kato function that is 1 on Q. It's 0 outside of 2Q. And it descends in a controlled way. Okay, so the picture is like this. Okay, and the estimates that you require is that on Q, this function eta of Q, I'm going to call it, is going to be 1. And it's going to be supported in 2Q. And need some more color. Okay, so eta of Q outside, this function is going to be 0. And the estimate is the usual one, namely that I control the L infinity norm and I control the gradient. Well, the L infinity norm I control in the usual way, actually by 1. And the gradient I want to control in a way, well, I have length of cube time to descend. So length of Q times the gradient should also be uniformly controlled by this constant C, which is of that type. Okay, and this test function like this, you constructed the quadrillion times in this lecture, and if you have forgotten how it works, you just flip back to some pages in the, or if you do it online, you just click on the footnote. Okay, so this function can be constructed. Now this is not the test function yet. Okay, to construct the TB test function, because this would just be, it would just be the same function for every operator on this cube. And I want to incorporate some features of the operator into the test function. And otherwise the proof is not going to work. Okay, so for this, just keep in mind we're in dimension 1. Okay, so the coefficients A, they are just a function mapping R to C. Okay, and what do we know about this function? Well, we know by ellipticity in one dimension reads as A being less than lambda and real part of A being larger or equal to small lambda almost everywhere. Okay, so it's a function that is bounded above and below. You would also call it an accretive function because it's bounded from below even in real part. Okay, and so the TB type test function that I'm using in the argument is going to be the following. I'm going to take B of Q to be A inverse, or this is just 1 over A, times eta Q. Okay, this is the function I want to use, and I call this 14.1. Okay, so you see, it's almost like just taking the test function that is a smooth indicator function for the cube, but we incorporate a feature of theta of t, namely we're going to incorporate the inverse of this annoying function A, which also appears in the definition of theta t on the right hand side. And that's going to be a vital information. Okay, so the rest of the argument now goes in 5 steps. Okay, and I will try to give some catchy titles to each of the steps, hopefully making it easier for you to remember what the whole plan or the whole strategy of this argument is about. Okay, so what is the first step? The first step is called accretivity of the test function. Okay, so accretivity estimate for the okay, and before I start really going in the proof, I should say once again, trying to jump in front of the camera, hi there. I should say once again that in contrast to most of the proofs I've been doing to you, where I try to outline before starting really the full strategy of what's going to happen, in this proof, it's rather take it as a learning by doing. Okay, take it as a learning by doing, as a first glimpse on this technology, so that when you go to the high dimensional case, you'll be fully prepared and you have this one guiding example to guide you through the more complicated proof in high dimensions. But it's completely natural that none of these steps will appear logical for you in the way that, in a sense that you would expect me to do them. Okay, so stay with me nonetheless. Even though each of these steps might be a surprise for you, it will assemble in the end. And once we've done it once, we're going to try to understand what we actually did, and then going through the high dimensional case is going to be much easier. Okay, so my first step will be what I call an accretivity estimate for the test function. Okay, and so my claim is that I can bound the following thing. I call this 14.2. I claim that I can bound the dyadic averaging operator acting on my function at position x. I claim that I can bound this in real part from below by a constant whenever x and t belong to the Carlson box. Okay, and this constant I can calculate, and let me try to recall what the constant is going to be. I guess in the end it's going to be lambda over lambda squared. Well, it doesn't really matter, it just shows you that it depends on ellipticity and it's a positive constant. Also in this proof I'm going to carry explicit constants through so that you see easier where we used different types of properties of this matrix A, or this function A in particular. Okay, so I claim that I have this lower bound for the test function on the Carlson region. Okay, so why should this be true? Well, here's a picture of a Carlson region. Okay, think of this sitting down here. This is maybe your cube Q. Then this is L of Q. And then the Carlson region is this kind of thing. And maybe this part and this part don't belong to the Carlson region. Okay, and so then there's x is here and t is here. Okay, and so take xt here. Now, how was the dyadic averaging operator be defined? At of bq at x is of course an average of bq y dy on some cube q prime. Now what was that cube q prime? Q prime was the unique dyadic cube of generation t that contained the point x. Okay? But because x is in q and t is less than the length of q, okay, it means that this cube q prime has also length less or equal to the length of q. All right? But then there's this dyadic structure. These cubes are nested. So if x is in q and I look for q prime, the unique dyadic cube of a generation at most giving cubes as large as L of q, then this q prime has to be a subcube of q. Okay, so q prime in this case would just be this one. Okay, and in general, we have that q prime is a subset of q because xt is in the Carlson box. You agree with that? All right, so that's good because we have not so much control. This averaging operator, when the t gets small, it takes ridiculously small cubes for the averaging. Okay, but we always stay with all of these cubes inside of q. And on q, we know exactly what the test function does, this bq, because on q, bq is just A inverse. Okay, so hence on q prime, because it's a subset of q, I can say that the real part of bq is just equal to the real part of A inverse. Here I'm using that q prime is a subset of q. Okay. And now this is just numbers, so real part of inverse of a complex number. This is real part of A bar over absolute value of A squared. And then I have a lower bound for the real part of absolute value, because it's just the same as if I would remove the conjugation, doesn't change real parts. In other words, this is larger than, numerator is larger than lambda, and denominator is less than capital lambda squared. So this gives me this bound. Okay, so it's even a pointwise bound on q prime. Well, if this function has pointwise bound by this constant on q prime, then I can also take the average everywhere and I compute the averaged bound. Okay, so I just take averaging on q prime. This gives me 14.2. average this one, you take real part in and out of the integral, and you get exactly this bound. Okay, so this is the accretivity estimate. Now, why am I so interested in proving this accretivity estimate? This is because of part 2, and part 2 I would consider to be the vital part of the argument on which everything that's going to follow is going to hinge on. Okay, and so this is not back to the future, but it's back to the dyadic averaging operator, so back to the past. Okay, back to the dyadic averaging operator. Okay, so what I claim, or what I want to do, is I want to produce an estimate of the form that the Carlson measure, or the measure of the Carlson region with respect to this density thing here, this should be controlled by a similarly looking quantity, but I reintroduce the dyadic averaging operator by bounding it from above by gamma t of x times at of bq of x squared dx dt over t. Okay, so I'm starting to kind of undo all of the steps that I did with you in lecture 13. Okay, because in lecture 13, one of the steps when we reduced to Carlson estimate was that we actually took this thing, we applied Cauchy-Schwarz, we throw this with a measure, we had an L2 bound with the dyadic averaging operator, and we said, well, okay, now this has to be a Carlson measure. Okay? Now I'm trying to do it backwards, and I want to produce an estimate like this. Well, the good thing is I can produce an estimate like this because this function, and this is absolute value of a product of two numbers, so it's just the product of the two absolute values. And this thing I even control in real part from below by this number. So this estimate is going to be certainly correct if I just put a lambda squared over capital lambda to the 4 on the left-hand side. Okay. And so this is just a constant. I could also multiply to the other side. So I'm back to bounding this quantity. Okay, so this is the step where I sort of link the Carlson measure estimate on this particular cube with the test function itself. And I'm not going to do it in a stupid way, just, multiplying the Kato function and saying, well, here's a 1 and I take a smooth indicator function, but I'm doing it in this very specific way. And the reason, and this at least when I saw these proofs for the first time, was when I honestly thought that whoever came up with this was truly genius. With this at hand, I'm starting to undo even more steps that I've done with you in the other direction last lecture. Okay, so this is gamma t times at. Okay, I'm gonna write it like this. Okay, let's put gamma t times at acting on bq at x. So now I'm doing the principal part approximation backwards. Okay, so now this is a thing we've done last time. Gamma t at, the approximation of theta by things that work as multiplication operators on each scale t. Well, what was principal part approximation? This was an approximation in a square function sense of our friend theta of t over there. So I bring back theta to the party like this. Okay? And then I'm gonna use this decomposition and I make it two terms on the right hand side. So what do I get? I start from here. Should I give this guy also a number? I think for later purpose, yes. So for later purpose, this is gonna be 14.3. So I start in 14.3 on the left-hand side, just copy and pasting it, lambda over lambda 4, integral over the Carlson box, gamma t x squared dx dt over t is bounded by, well, I just use a triangle inequality on the right-hand side, and I make it two integrals. Okay, so I make it a gamma t times at at x squared, minus theta t, okay, minus theta t at x squared plus, and I should apply it to BQ. Sorry, been slightly sloppy here. BQ at x squared plus theta t BQ at x squared dx dt over t. You agree? It's just a triangle inequality. Except that if you're very careful about this was triangle inequalities with the squares, so I should put a 2 here and then it's correct. Okay, and so now I'm very, very generous with all these norms, and I just throw away the fact that I'm integrating in space only on Q, and I make it global norms. But what I'm keeping is that integration in T does not give me the full square function because it does not go up to full infinity, but somehow the square function is truncated, and the truncation level on the top here is the length of Q, because this is where the Carlson box ends. Okay, so this is the length of Q, but inside I'm making it full global L2 norms. Gamma t at minus theta b applied to BQ, 2 norms squared, plus theta t BQ, 2 norms squared, dt over t. Okay. So why should this be any good? Well, this thing here, for this guy, I could even go all the way up to infinity, because this is the principal part approximation. Now I'm going to use the principal part approximation, because it even works when I integrate all the way up to infinity. This is a positive quantity, so here I get a constant times BQ in 2 norms squared, and then I have this remainder term, which I would call the truncated square function with theta t, which is this one. Okay, and you see that here I have to justify that I'm allowed to use the principal part approximation, and I'm allowed to do so because this function BQ over there is a bounded function with compact support, so clearly it's an L2, and I had this extension that in one dimension principal part approximation works for all functions in L2. So here I'm using Lemma 14.3. Okay, so you see I've done in backwards direction the whole work of the last lecture, but because I started with theta t applied, so to say, to the one function, and I had this accretivity estimate, I could reduce it to, first I need an L2 bound of this test function, and I need to control this. Okay, and now you should say, well, wait a minute. This is up to the truncation, but the truncation is arbitrary because I'm not telling you how large the cube is. This is the square function. You told us all the time that we have to bound in order to prove the Kato conjecture. So aren't we running in circles at this point? Well, the thing is that here I have to bound the square function just for this BQ function. And part of the game is to design functions for which I can bound the square function, the estimate of which is in question in the first place, manually, by bare hands, by design of the test function. Okay, that's the part of the game. Okay, so at this point you see I need two more properties. I need appropriated L2 L2 control, and I need the manual bound for the square function. And both should come by magnitude of constant times measure of the cube in order to make the proof work. Okay, so step number 3. Let's see, step number 3 should be easy because now I have to deal with these two terms here. So step number 3, okay, I mean it's easy. Do you think it will fit down there? I'm not telling you what the step is. I'm telling you the headline. It's L2 bound for the test function. Okay, so it takes care of this term over here. Okay, now you'll agree that it's certainly gonna fit in this line. For the numbering, this is always the thing I can never, even if I would learn the whole lecture by heart, the numbering I would still get wrong. So this whole estimate I'm going to call 14.4, and then 14.5 is this L2 bound. Well, I just have to bound the L2 norm of B of Q squared. Well, how large is this going to be? You see B of Q over there in 14.1, so this is less than the L infinity norm of A squared times the L infinity norm of eta Q squared, and then because the real part of A is already larger than lambda, the norm of 1 over A is less than 1 over lambda squared. And then eta of Q, we had a size estimate. Eta of Q in size is at most C, so this is going to be C squared times the measure of the cube. Okay, so that's my L2 control for the test function. Okay, and that's enough, right? I write it like this so that you see the explicit constant. That's enough because I want to control this whole quantity by the measure of Q, and here I have it for the first term. Okay, so what's the purpose with the other term? Okay, and this is now where you should... You have a question? Yes, yeah, you're right. If I would not insist on using the same C all the time, then here I could have just taken 1. Yeah, you're absolutely right. Okay. So for those following the videos who couldn't hear it, the question was, why did I take C and not just 1? And in fact, they are right. Okay, but C is also not wrong. Let's keep it that way. Okay, so now comes the interesting thing, because it's about this thing. Okay, and this has to be the hardest part, the estimate for the truncated square function. Okay, this has to be the hardest part because controlling the square function of theta t is what it is all about in these lectures. Okay, so it has to be a very specific function that allows us to bound the square function. Okay, and so in this step you'll see why I picked my TB type test function BQ exactly like this. So let's compute that guy. Okay, so theta t of BQ, what is it? Theta t is still on the board, the very left hand side. I'm just copying from there, so it's minus t 1 plus t squared L inverse diff A. But now I'm going to plug in the definition of BQ. BQ starts with A inverse. So it's A inverse eta q. Okay? And the crucial thing is that these two guys cancel. So I can write this as minus t, then the function I'm applying all my stuff to is the divergence. In this case is one-dimensional, so it's just a derivative. In any case, this is a smooth and compactly supported function, and so it's in particular an L2, so I can write straight resolvent like this. Okay, so I'm back to resolvent of L applied to a nice function, and the coefficients are gone. And now the huge difference is that when this A is sitting there, I have no choice than viewing it as a div A eta, and then it's a divergence form operator as it is, and there's no chance of computing it. But now the A is gone. Divergence of eta is just a derivative of eta. Of course I can compute it. I can tell you precisely where it is located and how large it is. Okay, and that's the game changer in this argument. Okay, so I should underline here that this is a smooth function. It has support in 2q, and it is bounded by, well, you have it over there. This time I really need the c. It's bounded by c over L of q. Okay. So I want to bound the square function. I just remove all dependence of L by using that M accretivity tells me that these guys, they are uniformly bounded on L2. Okay? So the estimate that I derive is that, let me give you some more space here. The estimate that I derive is that theta t bq in L2 norm is bounded by t times the divergence of eta q in L2 norm. Okay, that's sounds like a really stupid estimate, but why not? Let's take squares because we want to bound a square function after all. T squared divergence squared, and now I'm going to use and squeeze into my machinery of estimates all these properties of this function to control this L2 norm. So I get t squared times, I get measure of q twice, so this gives me 4 times c squared over length of q squared times the measure of q. Okay? And now something beautiful has happened. Because all these estimates, they are integration in dt over t. But all these families that we squeeze into these estimates, they are always uniformly bounded. Okay, that was the case when we did quadratic estimates and functional calculus. That's the case here. This theta t family is uniformly bounded in t. So these guys would have a uniform bound independent of t, which says that it's not helpful when t is small, and it says it's not helpful when t is big, but also it is no reason to believe that it would be impossible to bound a quantity like this. This is why one says that this is a singular integral. It's just on the edge, and you have to work really hard and find all these fine cancellation properties somewhere in space to make this integral convergent, whereas a stupid norm estimate would just give you 1 over t from 0 to infinity. And that's garbage. But now what has happened over there? What has happened over there? In this estimate I found a t. Okay, it's a t squared, which goes about a dt over t. Someone's watching me, okay. Okay, so this makes integration. Someone was over there. He was just staring like this. Okay, so there's a t squared here, and that would cancel the dt over t. So the singularity at 0 disappears. And because I truncated my square function, I can compute the integral. Okay, so let's do it. Let's throw an integral over 0 to the length of q dt over t over that whole thing. Throw an integral length of q dt over t all the whole thing. Throw an integral 0 length of q dt over t over the whole thing. And so what do you get? You get 4c squared. You get the constant. And then you get the integral. Dt over t makes just a t here. Now integrate t from 0 to length of q gives me a half length of cube squared. So times a half length of q squared. And so these guys cancel. This you can also make a 2 if you want. Okay? And you controlled manually the square function by the measure of q. Okay. So this was this step. All right. So should I give this a number? Told you the numbering is really not my strength. Yeah, I should give that a number and should be... Oh, wait. This was 14.4 already. Yeah, that's fine. So this should be 14.6. Yep. Okay, so this is 14.6. Okay, and now I can assemble all these estimates. And here's the conclusion. Now you have to just go and work backwards. Okay, so I have to use 14.3 because 14.3 says I can estimate the integral that I want to control up to constant by this integral with gamma t times at acting on the test function. Then we have used this over here to make it two integrals. Then we have bounded this one in here, and this one we have bounded over there. Okay, so I just need to use 14.4 and 14.6. And they give me that indeed the integral over the Carlson box of gamma t x squared dx dt over t is controlled by a new constant times the measure of q. Okay, and so in the conclusion, the test function has disappeared once again. The test function was just a means of proving this estimate on the cube. Okay, and so with this, the proof of the proposition would be complete. So what does that mean? What does it mean that I completed this proof? Well, I worked in dimension 1, but in dimension 1 I completed the proof of the Kato conjecture. Because I proved the Carlson measure estimate, which we already knew was sufficient and in fact also necessary for proving the Kato conjecture. So at this point, Kato conjecture in one dimension is settled. Okay, so at this point, Kato in n is equal to 1 is settled. Okay, and this is originally due to Koifman, McIntosh, and Meillet 85. Okay, the proof, the original one, is not the same that is the one in the lecture notes. Also, I should say the one in the lecture notes is not the same as in the original solution of the n-dimensional Kato conjecture, but it's our approach using, tricks that we learned over the last 20 years. Not me, but people I know learned tricks and they passed them on to me 20 years ago. Sylvie in a colloquium talk said 20 years ago I was still a baby. It's not literally true, maybe from her point of view, yes. But anyway, there's lots of experience in making this proof smoother. We try to make it as smooth as possible. But in spirit, the proof always remained the same. Okay, so in spirit also, this proof I showed you is kind of what they did in 85. Okay, so at this point, Kato is settled in one dimension. Let's make a quick break and then try to think about why it's so much harder when dimension is larger than 2, or larger equal to 2. Okay, so you've seen the proof of the Kato conjecture. I've kept, the final nail in the coffin for the proof of the Kato conjecture. I kept these four boards for you because I want to wrap up on the essential features in this proof. Okay, and you've seen that the proof worked because I was able to verify this T1 condition, which would be just the fact that I have the Carlson measure estimate, by using on every cube a different test function that I indexed with BQ. Okay? And so if we want to understand what I actually did, why it worked, and why it's going to be harder when dimension is not 1, I'll try to make a summary with you together to see what sort of properties we used for the test function. Okay? So let's wrap up the essential features of BQ. Okay? So first thing that you saw is that I employed a specific test function. At the end, I just proved some more thing, more than the Carlson estimate, that I reduced to on this one function. BQ, okay, it was not one function, it was one function for every cube, but still. Okay, so it's in the spirit of a TB argument. Now what was the things that I used for the test function? You see, there was one thing, property A, that came right after here in 14.4. At some point, we needed the L2 norm of B of Q. Okay, so it's L2 control. And this is what we did in 14.4. Okay, it's probably the harmless of all these things. Then the thing that got the whole machinery of estimate started, where I was able to do backwards all of the steps in the last lecture, but not for general function f, but for this very specific function BQ adapted to the Q, that was when after 14.3 the dyadic averaging operator was back in the game. Okay, and that was the starting point for all that happened on the other boards. Okay, so there was a pointwise control I was able to pointwise control of gamma t x by gamma t x times AT BQ of x on R of Q. That was what happened in 14.3. Okay, and then there was a third thing that happened after we reintroduced the principal part approximation and we used it to get to B of Q. All right, and that was that I was able to bound the square function with theta t of BQ. Okay, so point C was that I was able to do a manual control of a truncated square function with theta t BQ. Oh. Now when I wrote okay, it just reminds me that manual control sounds like driving a car with a manual control. And so now I can't get it out of my head. Anyway, that really confuses me now. Jesus, what's wrong? Okay, so I had a manual control of a truncated square function, theta t BQ, okay, by which I mean I was able by bare hands to bound that thing because I integrated it out over there. And an additional thing in getting there was that I used the principal part approximation with this function BQ. Okay, and principal part approximation with f being BQ. All right, and so that was in theta t BQ controlled by hand. That was what, 14.6? And principal part approximation, that happened in 14.4 as well. Okay. All right, so these are the three things that we used. Now let's try to think if these things potentially become more complicated when dimension is larger than 1. Right, on a very superficial level. So if you think about it, well, let's make a list. Because, you know, there have to be issues. Because Kato conjecture, I wrote it over there. One-dimensional case, 85. N-dimensional case took 15 years longer. Okay, so there had to be issues. So if you think of C, imagine I manufactured the perfect test function so that I'm able to control this square function by hand. I would still have to use the principal part approximation. So at least, you know, C would force me to construct the test function in the form of a gradient. Okay? So B should be a gradient. Okay. I mean, we don't know anything how I'm going to construct it. Let's pretend that it's not going to be a big issue to make a test function that looks like a gradient. Okay. So what do you think? And of course, when I construct test functions, I will do them in a way that I control the L2 norm. But what is really an issue is that the B thing. Okay? And why is this? This has to do with the fact that when I go to higher dimensions, then there's orthogonality. Okay? And what I'm trying to do here is I'm trying to control the norm of a vector by the absolute value of the inner product of two vectors. Okay? In one dimension, this is just all absolute values. When I go to high dimension, this is the norm of a c to the n vector, and this is a scalar product, and so this is an absolute value. Okay? And so to get a better feeling for that, okay, let's first write down that this is a huge problem due to orthogonality when n is larger or equal to 2. Okay, to see that, I mean, take x and t, some point in this Carlson box, and let's say omega. Do I want to call it omega, or do I want to call it xi? This I can never remember. Yeah, so let's call omega, or w, just call w gamma t of x. Okay, this is a c to the n vector. And let's call xi is also a c to the n vector. It's going to be the conjugate of the dyadic averaging operator. Okay, so I'm going to denote by xi bar component-wise complex conjugation. I'm going to note these vectors. Okay, so these are vectors in c to the n. Okay, and so what does the pointwise control say? The pointwise control says that we should have that up to a small constant that I can put there, I want to control the norm of the principal part by the absolute value of the inner product between the principal part and this vector. Okay? And clearly, an estimate like this, with a constant depending only on ellipticity and dimension, cannot be true when w is allowed to take values that are orthogonal to xi. Right? Then there's got to be cancellation. Okay, but when n is 1, then this is the same as saying that absolute value of xi is larger than c. Right? When n is 1, this completely decouples, and we proved this thing actually by using this pointwise lower bound even for the test function on the cube. But when there's multiple dimensions, then this means that, you know, this xi is my friend, because this is the thing that I can somehow design by design of my test function. I mean, I can try to design my test function so that its values are not spread all over complex space, but they take values in a very specific direction. But if I want this estimate, then I have to design test functions, the values of which roughly point in the direction of omega. Okay, so when n is larger than 2, then xi should roughly align in direction omega. I mean, xi and omega, they don't have to be parallel or, you know, linear dependent, but they can't be too far away in terms of angles. So that would mean that I have to design test functions for which I can say that the value roughly aligns with the direction given by w. But what was w? W was the principal part. And that's a big issue, because why am I doing this whole TB procedure is because I am just unable to compute t of 1. And t of 1, this is precisely gamma t applied to the unit vectors. I'm unable to compute this thing to an accuracy that is sufficient to proving the Carlson measure estimate. So if now I start saying, well, I don't know this guy well enough, but hey, let's construct test functions that mimic more or less the direction that this guy points in. That's never going to work. If I would be able to do that, why should I do this whole strategy in the first place? Right? And so that's the issue. That's the issue why Kato conjecture in high dimensions is so much more complicated than in one dimension. Okay, so let's here say, but we don't know W equal to gamma t of x well enough. Okay, so now there has to be a way out. Let's say what time says. Okay, so what's the strategy? So now if I start telling you about these ideas and then finishing the proof off in the last lecture, this is all gonna look so natural in a way, but it's just like this when you know what to do. Right, but you have to come up with these ideas, and this was really some beautiful mathematics that these 5 guys in the solution of the Kato conjecture were able to complete this proof for the first time. And then once there is a proof, then you can start asking for simpler proofs, smoothen out the proof and so on. But there has to be one starting idea. Okay, and the idea is that you adjust the test function to what you're trying to prove even further. Okay, so in the beginning it was t of 1, then it was t of b, maybe with a global function b, but that had to do something with the operator. Then it became t of b of q, where these b of q were test functions indexed by the cube, and that was enough for this argument. But now all of a sudden directionless plays a role in the argument. And the idea is simply to take directions into account when constructing the test functions by forcing the principal part to point into certain pre-specified directions. Okay, and I'm going to tell you how one can do that. All right, okay, just for the sake of completeness, I'm cleaning all the boards, but don't be scared, I'm not gonna refill all of them in this lecture. Okay. So, the idea will be that first we decide in which direction the principal part points, roughly, and only when we decided that, we're going to start constructing test functions. And that uses a sectorial decomposition of c to the n. Okay. So this is 14.2, I guess. Yes, the sectorial decomposition of c to the n. Okay, so the key idea that was brought in the game and then eventually led to the solution of the Kato conjecture in all dimensions was to use this sectorial decomposition on the principal part. In other words, we try to enforce the principal part to point on RQ to lie in a small cone. Okay. And the central axis, I'm going to tell you in a second, Okay? So cones around a fixed direction means that you do not deviate too much from that direction angle. Okay, so a cone around the direction psi would perfectly convey the idea that if omega would take values in a cone around psi, that you can hope for this sort of estimate. Okay, and so what's the precise definition of a cone like this? So 14.4 definition. So epsilon is a positive number here. Psi in C to the n is a unit vector. And then I'm going to call the open cone with central axis psi. This is for me the following set, denoted by gamma of psi epsilon. These are all complex numbers w except for 0, or all C to the n vectors except for 0, with the property that the normalized version of this vector minus the prefixed direction is small in norm. Okay? That's a cone. So, quite ironically, because C to the 1 is already a two-dimensional drawing, the only case in which I can illustrate the concept is the case where we don't need it because we already finished the proof. Okay, but I'm going to draw it in dimension 1 nonetheless to show you what these parameters mean. So this is 1, then there's a real part, and then there's imaginary part. There's 1, and there's 1. Then there's a circle going like this. Okay, then imagine that there's this prefixed direction psi. So psi is this unit vector pointing like this. And then what you do is you draw the cone by placing a ball of radius epsilon on the boundary, and then you take these intersection points and you turn them into a cone. Okay. Okay. So this is my cone gamma psi epsilon. Okay. So this is how these cones look like. Okay, so they fix directions. Okay, and so with these cones fixed, and epsilon, I should say, epsilon is still some sort of degree of freedom. Right, it's a thing that we can use to our advantage whenever we need. And of course, we try to make epsilon small. Okay, because if it would be 0, well, then we would basically pointing in direction psi all the time. Okay, so we want to take epsilon small so that the proof works. And what we're trying to prove at the very end is the following key proposition. So this is 14.5 proposition. I'm going to call it the key estimate, because this is what I saved for the last lecture. And yeah, please. Yeah, you could also rephrase the cone in terms of scalar products. Okay, you're gonna see. You mean in order to arrive here? Yeah, we do in the. So the question from the audience was, can I characterize it in terms of scalar products so that I see why this relates to this? At the point where we're gonna use the definition of the cone, I'm gonna make, of course, explicitly the calculation to show you that an estimate like this pops out, and it will be advantageous for us to define the cone like this. I hope at this point you can see at least that it conveys the same idea, namely that elements that satisfy either this or this, they have to be vectors that are close to the direction xi, so that the scalar product can either, you say that the scalar product has the lower bound, or here what you do is that you normalize to the unit sphere and then you compare with the other fixed unit vector and they have to be small. That is roughly the same as saying that they're close in angle. Okay? So, but thanks for the question, we're going to get there. Okay, so the key estimate is the following thing. There exists epsilon positive depending on just the things that I'm allowed to have it depend on. So n lambda and lambda, such that I can do the following thing. For every unit vector, so for every direction in C to the n, I have a Carlson measure estimate, but I only have the Carlson measure estimate when I throw away all the values of the principal part that do not end up in the cone. Okay, so in other words, I'm claiming I have the following thing. I have the integral r of q, I have gamma tx times the indicator function of the cone with parameters xi and epsilon at gamma tx squared dx dt over t less than c times q, and that happens for all dyadic cubes. Okay. See, so I throw away everything that is not in the cone. And this is what I'm going to prove on Wednesday. Okay, but it perfectly gives you this intuition that we force the principal part to take its values in this cone, and then the whole strategy, I'm going to repeat the whole strategy from the first part of today's lecture. I'm going to construct test functions adapted to the cube, but because I'm only working with this quantity, I have the additional freedom of assuming where the values of gamma t are roughly located in, and I can also use this epsilon to somehow steer the estimates the way that I want them. Okay, so I'm done in a second. I just want to show you that this will imply the Kato conjecture. Okay, this implies Kato in virtue of, what was it, corollary 1316. Okay, so I'm saying once I have that, I'm going to do Wednesday, then it's all done and we have solved, or we have shown to you the proof of the solution of the Kato conjecture. And so let's quickly see why the key estimate implies the Kato conjecture. Well, what we have to do is just to prove the Carlson measure estimate. Okay, so we just have to get rid of these cones. Well, by compactness, you can cover C to the n, except for the origin, which is not contained in any of these cones. You can cover this by a finite number of cones, gamma xi1 epsilon and so on, until gamma xi n epsilon, with n being a number depending on epsilon and n, and epsilon is just a number from the key estimate, so it's a fixed number depending also on the good parameters. Okay, this works just by compactness. You cover the unit sphere by these balls, you select finitely many, and then the cones cover C to n without zero. Okay, so you can cover the values where the principal part sends the x and the t's to by these cones, and then you start with the Carlson estimate that you want. So it's r of q gamma of t x squared dx dt over t, Well, either this is 0, so there's nothing to do, or it's not 0, then this is in one of these cones. So this is certainly bounded by r of q times taking the sum from j to 1 to capital N over these restricted principal parts, restricted in terms of direction. Okay, so gamma t of x squared dx dt over t. Okay, but then you can throw the sum out. You use for every cone, you use the proposition. Then you get the bound by the constant from the proposition times the number of summons here, but this is just n, and this gives the Carlson measure estimate. Okay, so that would be enough. So I close at this point for today, and then we're going to see each other one last time on Wednesday. And I hope to be in better shape on Wednesday, because it's going to be a hard but beautiful last lecture, and we're going to prove the key estimate. Okay, so for the Wednesday lecture, this is just for you guys here. Please keep the terminology in mind, because I will not have the time, like I did today, to recall all of the things that somehow led to the starting point of the lecture. Okay, so I'm going to jump right into the proof. Okay, that's it.